there, it's Mrs. Tremblay, and I'm here to help you out with your math skill assessment number 15. We're going to finish covering the chapter on probability. So we're in section 9.3 and 9.4 in your textbook if you're interested. This is part of the assignment, so you do need to watch and listen to these notes and write down everything that I write down so I know that you saw this. All right, so first thing we're going to talk about is experimental probability. We've talked already about theoretical probability, which is what should happen, and experimental probability is kind of like what actually happens. It's probability that's based on repeated trials of an experiment. So that means you're actually trying it. Like, for example, flipping a coin, we say there's a 50-50 chance, right? You can flip heads or you can flip tails. That's in theory what should happen. Experimental probability would be, okay, actually flip this coin a whole bunch of times and see what I get. It's calculated kind of the same way. The probability of the event, so that P just means probability of, is equal to the number of times that the event occurs, so the number of times it actually happens, and we're going to divide that by the total number of trials. How many times did you try it? So how many times did the outcome happen that I'm looking for, and how many trials did it take for it to happen? And usually it's given as a percent. So we'll start off writing our answers in ratios, and then we'll change them to percents after that. So we're just going to move right into the examples here. And I have a little bar graph for you to look at. It says use a bar graph to find the experimental probability. And we have drawing a marble. So there are a whole bunch of marbles in a bag. Doesn't that sound like a fun game? So we collected some data on that. And we have blue, red, green, yellow, orange, and purple marbles that are all in here. And this tells us how many times the color was drawn. Number one, I ask you, what is the experimental probability of drawing red? That means in this experiment, how many times did we draw red? When you're giving me the probability of this, you actually have to find out the number of times you drew red, and then we have to put that over top of the number of trials. So first off, in looking at the graph, we can see that, okay, here's red. I follow it up. I follow it over. I can see that red happened 6 times. So I'm going to write down 6 in my numerator spot because that is the number of times the event occurred. Now I need to know how many trials. I'd like you to think for a second. I'll tell you eventually, but how can I figure out the total number of trials? Hopefully you said, well, look at the bar graph and see how many total trials there were. For blue happened 4 times. We already said red happened 6. Green happened 4. Yellow happened twice. Orange happened 3 times, and purple happened once. So if I want to know how many times red happened out of the total number of trials, what you need to do now to find that denominator is just add up all those. They're called frequencies. So 4 plus 6 is 10, 14, 16, 19, and 20. So marbles were drawn 20 times. 6 of those times, they were red. All right, so you can give me the answer as a ratio. If you did, I wouldn't want it to be 6/20ths. I would want you to simplify that into 3/10. And honestly, you'll probably give it as a percent. You'll be asked to give it as a percent. So to change any fraction into a percent, you just do top divided by bottom, so 3 divided by 10, and we're going to multiply that by 100 to get 30%. All right, so acceptable answers would be 3/10 or 30%. Don't give me 6/20ths. That's not in simplest form. Okay, number 2, I want to know the theoretical probability of drawing not yellow. I know it seems weird. What's kind of nice is we're dealing with the same data set, so I know that it's out of 20. And now I want to know how many of these trials were not yellow. Well, here's yellow. 2 of them were yellow. So if there were 20 trials and 2 of them were yellow, how many weren't? Yep, 18. And if I asked for that as a ratio, you could simplify that and just say, okay, 9/10. If I asked for it as a percent, you could just multiply that by 100. 9 divided by 10 times 100. And 90% of the trials were not yellow. All right, number 3, I would like to know the theoretical probability of drawing a color with more than 4 letters in its name. So more than 4 letters in its name. Does that include blue? No, blue has 4 letters in its name, so that one's out. Red does not have more than 4 letters. No. Oop, green has 5. Yellow definitely has more than 4. Orange has more than 4. Purple has more than 4. So if I want the probability of drawing a color with more than 4 letters in its name, we're talking about green, yellow, orange, and purple. So on the top, I need the number of times that occurred. It occurred 4 plus 2 plus 3 plus 1. So 4, 5, 6, 7, 8, 9, and 10. This happened 10 times. Out of how many? That's right, still 20. And a better way to say that as a ratio would be 1/2. So if I asked you for your answer as a ratio, that's what you would give me. If I asked for it as a percent, you would take 1 divided by 2 times 100. I'm sure you know 1/2 is 50%. But that's the process. Top divided by bottom times 100. All right, so we're moving along to students. Instead of talking about marbles, we're going to use a different example here. They're not all about marbles. A lot of them are. It seems like with probability, there's always marbles in a bag. I'm not sure why. Okay. There are 25 students' names in a hat. You choose 5 names. 3 are boys' names and 2 are girls' names. How many of the 25 names would you expect to be boys' names? Okay, so basically, this all has to do with ratios, which you're really good at. We've been doing it all year long. But you're expected to use an experimental probability to make a prediction with this. So I want to say, okay, this happened. Because this happened, what do I think is going to happen? So here's the deal. I know that there are 25 names in the hat. We chose 5, and 3 are boys and 2 are girls, right? I want to know how many you expect to be boys. So what I'm trying to figure out is how many boys' names out of 25. Right? So B over 25. You could use X if you want. It's fine. So we're going to compare that to another ratio where the top represents boys and the bottom represents total. We're going to use this to help us make a prediction. So it says that you chose 5 names, right? And 3 of the names were boys. So 3 out of the 5 were boys. Right now I want to know how many out of 25. So I'm going to use this 3 out of 5. And you might be thinking, what about the 2 girls' names? I'm not trying to figure out how many girls. I'm trying to figure out how many boys. So I want this 3 because the numerator represents boys. Do you recognize how to solve this? Please say yes. All right. B times 5 would be 5B. 25 times 3 is 75. Divide by your 5. And based on what happened with our little bag, it looks to me like there are going to be 15 boys in the class, or in names in the hat. I guess it never said it was a class. So again, with this, you're given one of the ratios and you're asked to figure out one part of the other one. That screams proportion. All right, last one in 9.3, then we'll move on to 9.4, because oh yes, there's more than this. All right. You must stop at 3 of 5 stoplights on a stretch of road. How frustrating. At least it's not 5 out of 5. Do you ever get your parents get stressed out, caught at the light? I am guilty of that. All right, so 3 of the 5 lights, you're on a stoplight. You're stopped. If this trend continues, how many times will you stop if the road has 10 stoplights? So you're given something that happened, and you're asked to make a prediction with it. So first off, let's figure out what we're trying to figure out. It says, how many times will you stop if it's out of 10? So I want to know how many times I'm going to stop out of 10. I just put X over 10. This is the number of times out of 10. That's what I'm trying to figure out. The ratio that you're given, it says you have to stop at 3 out of 5. So this X represents the number of stops, right? And this says you had to stop at 3. And the 10 represents the total, so it's out of 5. Now, right now, some of you are looking at this and you're like, well, hey, 5 times 2 is 10, 3 times 2 is 6, and you've got it solved. Some of you are like, what are you talking about, Mrs. Tremblay? If you're looking at this like, what are you talking about, Mrs. Tremblay, then cross multiply. 5 times X is 5X. 10 times 3 is 30. Divide by your 5, and you get X equals 6. So, based on this trend, if you stopped at 3 out of 5 stoplights, that if there are 10, it's going to keep happening, you'll have to stop 6 times. And that's what experimental probability is kind of used for. It's used to help us make predictions. All right, turn your page. Now we are on to independent and dependent events. All right, so first thing, you kind of need to know what those are. That would be very helpful. Two events are considered to be independent events if the occurrence of one does not affect the likelihood that the other will happen. So, an example of this, if you flip heads on one coin and tails on another coin, they really have nothing to do with each other. Just because you flipped heads on the first coin, the second coin's not going to say, oh, you already got heads, so I'm going to flip tails. They're not related. They're independent of one another. So if one event doesn't affect the other event, it's considered independent. Two events are considered to be dependent if the occurrence of one does affect the likelihood of the other one. For example, let's say your teacher chooses one student to lead a group, then they choose another student to lead another group. This would be dependent, because if you already chose that first student to lead the one group, that student cannot choose to lead the other one. So what you did the first time affected what happened the second time. So that's an example of something that's dependent. And we're going to learn how to calculate the probability of independent events and how to calculate the probability of dependent events. There are a few ways to do this. I'm going to focus on just one because this is the condensed version, of probability. So if we're dealing with independent events, you should box this just like that. When you're dealing with independent events, the likelihood that they're going to happen, the probability of two independent events, event A and event B, is the probability of A times the probability of B. And we know that the probability of something is the number of times it happens out of the total number of times the experiment took place. So the little formula for this, you basically, to get the probability of the events happening, the first event and the second event, probability of both events, is equal to the chances of the first event happening times the chances of the second event happening. So let's try an example of this so this big formula can make sense here. It's not that complicated, I promise. An example. You flip 2 quarters. What is the probability you will flip 2 heads? The first thing you have to understand is that this is independent. Flipping a coin, what you flip the first time has no effect on what you're going to flip the second time. Just because you flip heads the first time doesn't mean you're going to flip tails the second. But I want to know, what are the chances that you are going to flip 2 heads? Okay, so to figure this out, I want to know the probability of event A, and I'm going to take that times the probability of event B. So when you flip a coin, how many outcomes are there? What could happen? You could flip heads, or you could flip tails, right? So there are 2 possible outcomes. The probability that you're going to flip heads is 1 out of 2, because one of those sides is 2, right? So if I want this to happen twice, event number 1 is you'll flip heads. Event number 2 is you're going to flip heads again. All this is saying is take the probability of the first and multiply it by the probability of the second. So this is the chances it's going to happen the first time. This is the chances it's going to happen the second time. So the probability that you're going to flip 2 heads is 1 times 1 is 1. 2 times 2 is 4. You have a 1 in 4 chance at that happening. So when you have 2 independent events, to figure out the likelihood of those happening together, both events happening, you just multiply the chances of each of them happening by one another. And you could give it to me as 1/4. Sometimes you'll be asked to express it as a percent. If you were, you would take 1 divided by 4 times 100. Or maybe some of you look at that and you're like, I know that's 25%, 1/4 of 100. All right. Either one would be acceptable. All right, now the probability of 2 dependent events happening is pretty similar to this. It's not exactly the same, but it's really similar. So if you have 2 dependent events, meaning one of them, the first one, has an effect on the second, to figure out the probability of both of them happening, you take the probability of the first event and you multiply it by the chances of the second event happening after the first one occurs. So again, I think this example will help. You're still multiplying here. You're multiplying the probability of the first and you're multiplying the probability of the second. But with the second, it's not going to end up being the exact same fraction here. So the example for this one. A vase contains 7 purple flowers, 9 yellow flowers, and 12 pink flowers. You randomly choose a flower from the vase to take home. Your friend randomly chooses another flower from the vase to take home. What is the probability that you choose a purple flower and your friend chooses a yellow flower? Okay, that's a lot of words here. The main focus is I want to know what are the chances of me picking a purple flower and my friend choosing a yellow. What I'd like you to think about right now is what makes this dependent. These are dependent events because whatever flower I pick, I'm not putting it back, am I? I'm taking it out, I'm not putting it back in, so my friend can't pick that flower. That's what makes this dependent. So I need to multiply the probability of the first event by the probability of the second event. The first event, it's the probability of the purple flower. So we need to figure out what are the chances of drawing a purple flower. Well, how many purple flowers are there? That's our numerator. When you look back up at the paragraph, it says there are 7 purple flowers. So that's the events that could take place here. Now, out of how many? Because probability is written as a ratio, right? So I need to know how many flowers there are in this vase. Well, there are 7 purple, 9 yellow, and 12 pink. So you need to put all those together. And when you put them all together, hopefully you got 28. That's what I got. And we're going to simplify that before we work with it. So 7 28ths, 7 goes into 7 once, 7 goes into 28 4 times. So the probability of the purple flower is 1/4. That's the probability of event A. Now we're supposed to multiply that by the probability of event B after A happens. So I want the probability of a yellow flower. And the first thing you need to know is how many yellow flowers are there to pick from. And it looks to me like there are 9 because I chose a purple one. So 9 is going to be my numerator. And now it's not over 28. How many flowers are left? I took one, right? So when I took the purple flower, that means there's only 27 left. So the chances of your friend picking a yellow one are now 9 out of 27, which of course simplifies to 1/3. So if I want to know the probability that I choose a purple and my friend chooses a yellow, I'm going to take the probability of my event and multiply that by the probability of my friend's event after I picked my flowers. And 1 times 1 is 1. And when you multiply your 4 times 3, you get 12. And if you wanted to change that to a percent, I might ask you for it as a ratio. And if you give it to me as a ratio, 1/12 is great. If I say, hey, give me that percent, then you're going to take 1 divided by 12, multiply it by 100. And we actually have to round it. We get 8.3 repeating. So I'm just going to say 8.3 repeating percent. Pretty slim. The chances of that happening are pretty slim. All right, so go buy yourself some flowers and test it out. See you later.